Welcome to the ILR Summer UF Research Student Presentations. Today, Jordan is going to speak to us, and you can see on the screen their subject, but she received her bachelor's degree at UF in environmental engineering from the Wertheim School of Engineering in 2023. She's currently a third-year PhD student in the Environmental Engineering Science Department in the Engineering School of Sustainable Infrastructure and Environment, which is a long name, studying sustainable materials management and beneficial reuse of industrial wastes, which we need to learn how to do. Jordan, thank you for coming to speak with us today.
Thank you, Walter. Appreciate that. All right, let's see if I can figure out how to use this. So, can everybody hear me okay? Is this fine? Real close to the mic. Maybe I'll just hold it. Yeah? Okay. Good. Thanks, guys. So, my name's Jordan. I study a lot of different industrial wastes and how we can reuse them instead of just throwing them away. But one of the wastes that we've been looking at closely that has been a little bit controversial is phosphogypsum. So I'm going to talk about what that is and how we're trying to reuse it and why it's important to reuse it instead of just kind of leaving it as a waste. All right, I'm going to try and use this clicker. There we go. Okay, so I'm just going to go through kind of the whole process of what we've been working on. So I've been working with Dr. Tim Townsend at UF in the Sustainable Materials Management Lab for about 5 years. I'm a third-year PhD student, but we've been working on this project for a long time. So as you can imagine, there's been like lots of steps for this process. So I'm gonna kind of walk you guys through the introduction and problem statement, and then we're gonna go through, you know, the proposed solution and how we could get that solution approved, and then finally what we're actually doing. Okay, so phosphogypsum, I'm going to refer to it throughout the presentation as PG, phosphogypsum PG. It's a byproduct of the phosphate fertilizer industry. So through the process of making phosphate fertilizer, they take this phosphate ore, which is mined, they add sulfuric acid to make phosphoric acid, and then fertilizer comes out of that as the product, and then a byproduct is phosphogypsum and processed water, which is acidic because of that sulfuric acid. So that's kind of the process you can see here. There's water, there's sulfuric acid, and then phosphate in the phosphogypsum. PG is stored in gyp stacks because, as you can imagine, the phosphate ore has trace amounts of radioactivity, which radium is a naturally occurring in soils and in, you know, rocks. So when you take that phosphate ore and you add sulfuric acid to it, you make a slightly radioactive and acidic product. You can't put that in a landfill. So right now, the way that we dispose of it is by putting it in these giant stacks called gyp stacks. And that's what the picture of the one on the top is, a top view from Google Maps. So you can see it's like a giant stack with a pond on top of it. And the pond is the process water. So it's a little bit acidic. And it's also just rainwater and any other wastewater that ends up in there. And then this other photo is a side view. So you can see how tall the stack is. It looks like a landfill made of sand. It's just a really big stack of phosphogypsum. There's over 2 billion tons of PG stored in these stacks in the US, and there's another 280 million tons being produced all over the world each year. So clearly this is a problem where, you know, this stuff is stored in stacks, and it would be really great if that wasn't the case. A similar issue that you may have heard of is Piney Point. So in 2021, there was a gyp stack in Tampa called Piney Point that had a leak. And tons of gallons of water had to be pumped into Tampa Bay, and it caused fish kills and red tide, like algal blooms. And there was just a lot of like hubbub and controversy around that. So you may have heard of it. And I wanted to bring it up because this, I think, paints a very clear picture and kind of motivated part of our project that we're working on right now, because this issue really like caused environmental problems, and it just made it very clear that the gyp stacks are not a long-term solution. They're something, you know, we're storing them here for now, and the plan was that it would be indefinitely stored in gyp stacks, but really that's not a solution. You can't just put a bunch of dirt in a pile and then walk away from it. So what happened at Piney Point was basically there was a leak in the liner, so the top of the gyp stack was lined where the pond was, because it was no longer being used for putting more phosphogypsum in the stack. It was just kind of sitting there waiting for who knows what. And there was a break in the liner, and the water started to leak out. And because of that, they decided that they needed to pump the water into Tampa Bay so that it wouldn't go into the surrounding communities. So they evacuated around 300 homes and businesses in the surrounding area, and they pumped all of this water into Tampa Bay. And you can imagine it's a byproduct of phosphate fertilizer. So you're pumping this nutrient rich and also slightly acidic liquid into the bay. There's obviously going to be some issues. So the plan with this Piney Point gyp stack now is that the water is actually being dredged out and deep well injected. So it's going below the aquifer to be treated naturally by the environment. And the plan is that it will eventually just be grassed over. So they're going to put another liner over it, and they're going to just close the gyp stack completely. But you can imagine that there's still going to be a stack there. And while we might be able to use that land again, there's going to be some restrictions to that land use. It's still going to be like a mountain. Like you can imagine if you were to cover a landfill, it's kind of the same sort of thing. So a little more about phosphogypsum. I mentioned that it has a slight radioactivity and it has a low pH, but the core of this product is calcium sulfate, which is a beneficial material. It's okay. Sorry. That's okay. Well, it's a beneficial material. Calcium sulfate is basically gypsum, and that's what like drywall is made out of. And not only that, but oh yeah, can I skip forward or? Yeah, I can just go forward from here. Thanks. Okay, here we go. All right, so we're at calcium sulfate. That's the core of this product, but there's also a low pH from the phosphoric acid. There's small amounts of radioactivity from naturally occurring radium in the soil and in the phosphate ore. And then there's also some COPCs, which is constituents of potential concern. That means things that could interact negatively with people or the environment. So some of these are anions like fluoride and sulfate. If you have too much of that, there's going to be some issues. And that's too much to get into right now, but you can imagine things like metals, arsenic, which you've probably heard of. Some of those materials or elements can be present in PG. So that's why this stuff is not used for anything right now, and it's stored indefinitely. And there's also regulations around it. So clearly it's not a great product that we can just throw anywhere we want. There has to be some regulations. It's not a hazardous waste. The Resource Conservation and Recovery Act exempts it from being a hazardous waste, but it still is radioactive and it has a low pH. So because of those factors, reuse and research and development are limited on PG. But recently, there was an allowance by the EPA that said that people can use 50% of it in construction projects or in reuse projects, as long as the radioactivity is low and you know, it's 50%. So you can't just throw all PG in there. You have to blend it with something else. So the project that you may have heard of that I'm working on is in Tampa. It's by the Mosaic company, and they test their PG in the stacks for radioactivity all the time. And so it is below the radioactivity of it is below the threshold that EPA set as the allowable amount that you can use. So that's a good sign. That means we're on the right track to reuse it. And I want to give a little bit more information about the radioactivity. So radium-226 is the element that's in this PG. It's naturally occurring, so it's actually everywhere. It's in soil and rocks, and it's in the ground, which is where we get the materials to make phosphate fertilizer. And now I'm kind of beating a dead horse, but I think you guys understand it's not like people aren't making this stuff radioactive. It's naturally radioactive, and if we want to keep making fertilizer, we have to figure out what to do with it. So you can imagine the problem. On the one hand, PG is stored in gyp stacks. Storage can lead to spills, and also that radioactivity is not kept in those stacks. There still could be radon gas forming from the decay of the Ra226. So it's not a long-term solution, basically. On the other hand, when it comes to construction projects, in America, we're always constructing new roads, new buildings, new infrastructure. And these resources that we use are either mined or we buy them from somebody else. So they would have to be shipped to us. And so that leads us to the question of what would PG reuse look like if we didn't have to keep this in a stack on this next to the Tampa Bay? What would we do with it? So that leads us to the solution that we have in mind, which is putting this stuff into a road base. So I'm gonna use my little laser pointer. Here's the map. Here's a chart of the typical road. Okay, so when you're driving on the road, you're driving on the asphalt layer. But what's underneath is what's gonna stabilize the asphalt layer on the top to make it so, the road doesn't collapse. Are you trying to tell me something? I'm sorry. All right, so underneath the asphalt layer, there's a layer of base course. I'm gonna refer to that as road base. It's usually, about 10 inches, and it has to be pretty strong. So there's a lot of tests that need to be done to make sure that it's strong enough. But also there's some consideration of we're putting this stuff on the ground, so we don't want it to have a lot of contaminants in it. But on the other hand, you're putting it under a layer of asphalt. So we'll talk more about that, but this is the general idea, is to put the PG in this layer in a 50% blend with something else that is already used as a road base. All right. I think you have to click the screen again. Thank you. All right, so here it is again. This is what we do at our lab. This is my student, Noah. He's really awesome. He's a civil engineer, and he's doing a test here called Proctor compaction. So we basically took the PG and we took lime rock, because typically lime rock is what's used as a road base material. We took those and at a 50-50 blend, mixed it together, added a little bit of water, and then we used this machine here. It's basically a big hammer right there to smack this repeatedly. And that's the Proctor compaction test. So we did that. And then we end up getting this. And this little piston is for the test, which is like the final answer. It's called lime rock bearing ratio. So if typically what we put in the road base is lime rock, then everything else that we could possibly use as a road base, we're comparing to lime rock. That's basically what we're doing, but it is a Florida Department of Transportation method. So this piston goes into the sample after it's been compacted and determines how strong it is, basically. So we're not making concrete, we're just compacting the material. And that's what would happen if you were to put it in a road. So when you build a road, before you put the concrete on top, you put something else down and you compact it so that it's really strong underneath and it'll support the road base layer on top. I'm not going. Thank you. Okay, and I wanted to show you guys this photo, just a flooded road or standing water on a road. And there's been some confusion in kind of our reuse sphere of if we put phosphogypsum or any other reused material underneath an asphalt layer, we're putting it into the environment. What about when that gets wet? Like, what about when it rains and then water goes through the road and then water goes through the layer of PG and goes into the aquifer? And so this is kind of my response to that, is that asphalt doesn't have a very high permeability, and a lot of the water is really not going to go through the asphalt layer. So when you're driving on roads on the interstate or anywhere, you'll notice that they're slightly sloped. And that's because we understand that the water needs to go away from the road. It's not going to go through the road. It's going to run off and go into the ditches or whatever. So this is an example of a road that isn't built very well. There's no slope to it. And so the water is just sitting there. And it's not going to go through the asphalt. It's going to evaporate or it's going to run off eventually. So that's to show that the water that goes to the top of the asphalt typically is not going through the asphalt, which means that anything that's underneath it, meaning the road base, is not going to have water going through it either, or not a significant amount of water. And so any constituents that are inside that PG road base are not going to be leaving it. This is kind of another example of that. This is how we model it in my lab. We use a model called IWEM, Industrial Waste Management Model. And it was designed by the EPA, but it basically helps you predict if you have an infiltration rate, which is coming from the rain. So we have like the infiltration going through the road would be a % of the precipitation. Going through the road, going through the base layer, this is where the PG would be. You're not going to have a lot of water going through here at all, but any water you did have would need to go through all of these layers, and then it would be diluted in the groundwater before it goes up to the monitoring well, and then this is where we're going to be testing it. So that's just an example. There's a lot of layers of control and just dilution and attenuation that the water would have to go through, and any constituents in the water would have to go through before you actually get to having an issue. And I also want to mention that in this picture, clearly the monitoring well looks very close to the road, but this project that we're doing is next to the gyp stack. So we're building the road out of the PG that we're going to take from the gyp stack and put it right next to the gyp stack on the ground and then put asphalt over it. Nobody's going to be drinking the water right there. So we just have monitoring wells to do exactly that, to just monitor the, any constituents that are coming from the water. And that's typical at landfills or at any sites where there's any sort of waste being stored. Typically, you'll have monitoring wells to just check the water and make sure that there's FDP compliance or EPA compliance. Okay, so when you go about designing this road and proposing this solution, as the engineers, we had to go through multiple steps. So the first step was we had to do a risk assessment where we look at this material that has some constituents of potential concern that could pose some harm, like you don't want to eat it. It might hurt you if you eat it. So there needs to be some limits to putting it in the environment. And so that's where the risk assessment comes in. Then we do physical testing, which is the Proctor compaction and the LBR that I showed you a picture of earlier. And that's just saying that, oh yeah, we can actually use this. It would be strong enough to put underneath a road and have a stable road. Then we have to get government approval. So since it's a product going into the environment, the EPA and the FDEP have to approve it. And then the Department of Transportation also needs to approve, or really they just need to give their feedback, because we're building a road. We want to make sure that, you know, we're thinking of everything we can, because this is going to be a pilot road. It's going to be like a practice, just a test road. So we want to make sure we're thinking of everything we can, and we're asking all the relevant stakeholders what we should do and what we shouldn't do. And then finally, we have to design the road. So we have to think about what we want to test for and what materials we want to incorporate and how much material we need. And then we need to think about getting a contractor to build the road for us. So here's some pictures of the risk assessment. This is the environmental side, where we're actually going into the lab and we're looking at what is in the phosphogypsum or any other materials. So we'll typically do a leaching test, and that's what this one is. So leaching is just when you contact the solid with water and you see what comes out of it, comes out of the water basically. So that's kind of similar to if you were to put this stuff in a lake and then you test the lake water and you see what comes out. We do a ratio of like 10 times as much water as solids. So it's, you know, once it gets into the groundwater, there's going to be way more water than that. But if you were to think about the material coming out right below the surface of the base layer, or right below, there might be less water. So anyway, that's kind of a conservative measurement, but we think about all of these when we do our modeling and our planning. So the other factor is direct exposure. And this is thinking about if humans were to be directly exposed to the phosphogypsum through dermal exposure, through inhalation or ingestion, how would that affect us? And so we look at the total contents of the phosphogypsum, and we look at also if we blend that with the road base. So in this situation, since we're putting this underneath an asphalt layer, really leaching to groundwater is going to be our main consideration. Direct exposure, we kind of only need to consider at the moment when people are interacting with the material, like when they're mixing it up to put in the road base. But when we did this, we found totally normal and fine values. I won't go too into them because it's just kind of a lot, but like I said, there's a little bit of arsenic and strontium and fluoride in PG, but when you blend it and when you do all the modeling and you complete the risk assessment and you're really assessing not just what is in the material, but the total risk associated with everything about the material and the reuse situation, we found that you could use it. And that was our beneficial use determination study. So there was another risk assessment that was performed by a contractor that I just want to make sure you guys understand that this isn't really like a radioactive product, even though that's kind of how some of the news is trying to spin it. So a contractor did an independent study. They published this in 2019, and it was like very long, very in-depth research, but they basically just compared any users to this road and how their exposure would compare to background levels and the EPA's like risk management goal dose equivalent. So this table kind of shows that if you had a construction worker building the road, their exposure would be below annual natural background radiation exposure. So like I said before, radon and radium is naturally occurring in soil, and then radon gas is the decay phase of that. So when you have these things naturally occurring, there's going to be natural background levels that we all experience. And so working as a construction worker, you're still experiencing less than your background dose in a year. And that goes for every other user of the road and everybody working on the road. So a motorcyclist driving on the road, somebody driving the truck that has the PG in it. somebody living 50 meters or 50 feet from the road, which is very close. And like I said before, it's a test road at the phosphogypsum plant. So there's not going to be somebody building a house right next to it right now. And then a utility worker. So these are actually like very low compared to background levels, natural background levels, and compared to the EPA's risk management level. And this is kind of that spelled out, and then also to put into perspective. So MREM is a measure of humans, kind of like humans' interaction and exposure to radiation. So you can just see, if you were to get a CT scan, you're getting exposed to 1000 MREM radiation at one time. Natural background for everybody is around 300. And then if you were living in Denver, because of the elevation, you're going to have 80 more than natural background. A mammogram is 72. And then 1 year of driving on a PG road as a bicyclist, you're only getting 1. So you can kind of see how it's sometimes blown out of proportion when we say, you know, is Florida going to have radioactive roads? Well, Florida right now has a radioactive pile of dirt next to the ocean. So anyway, after the risk assessment, we did more physical testing, which I kind of already told you guys about. And I want to show you another picture of my students. They're really awesome. They're undergraduates. So that's our physical testing. Ready? And then after we wrote all of this up and we sent it in, it was time to get approved. So we wrote a beneficial use determination. We call it a BUD, where we outlined this risk assessment. We talked about everything that we did and everything that we found. And then we said, based on this research, based on these results, we think that we should be able to go to the next step, which is building a test road. So it doesn't mean that we're going straight from the lab to putting this, you know, right outside everybody's home, but it means that we tested it in the lab, we've thought about all of the factors, and now we want to try it in the real world on a test scale, small scale. So that's why we're putting it at the PG site already. And then the EPA wrote us back about 2 years later, and they granted permission for us to build the road. So that was at the end of last year, about 7 months ago. And at this point, we're almost ready to start construction. Okay, so this is what the road is. This is where it is. This is the stack I showed you earlier. The PG that would go into the road would be taken from right here, and it would go here. So this is the gyp stack. This is another gyp stack that is not being added to anymore. And this is where the fertilizer is actually made. So that's the plant. When you drive into the site way over here, there's a big sign and a gate that says you're entering Mosaic Company fertilizer plant. So nobody's going to be going in there that doesn't work there or, you know, is associated with the site. And all along this, there are groundwater monitoring wells. And there's also wells like spaced sporadically around the site that they're constantly monitoring for groundwater, any impact to groundwater and human exposure. So to design the road, we had to think about how, obviously, if this is a scientific experiment, we have to have a control to compare to, and we have to have our test sections. So we thought, well, we want to be able to compare to what we're already using, and we want to be able to have test sections that are a typical road base. So we ended up deciding on 4 sections and then 4 controls, and then the red dots that are really tiny are the groundwater wells. So they're going to be right next to the road. And then this is kind of what I showed you guys earlier with the layers of soil under the asphalt, but this is just more of actually how we designed the road in, you know, engineering drawings. Another cool thing about this road, this is actually a really important aspect, but it's a little bit hard to explain. But when you think about the water that could possibly be going through the asphalt, and you think about how probably not that much is going to be going through, that's something that we think about a lot in our lab. And to be honest, there hasn't been a lot of research that proves that not a lot of water goes through asphalt. We have information about the permeability of asphalt, and we have information about the groundwater once it gets underneath the road. But what if we could look at the exact amount of water that goes through the asphalt in a real world scenario? You can model that in a lab pretty easily by doing permeability tests. But it's really it's challenging to get that in the real world. So what we're going to be doing is we're building these lysimeters. This is two different views of it. This is a cross section, and this is like from the side, I guess. So basically, if the road is here, we're going to be putting a liner underneath the base to see exactly how much water goes through the asphalt layer and through the base layer. We're going to be able to take out any little drops of water. We're going to be able to extract them and then analyze them. So we're going to be able to look at not only exactly what is in that water that's coming through the base layer, if any, but we're going to be able to see the flow rate. So let's say every 3 months, we're going to go and check these lysimeters, and we're going to be checking the groundwater monitoring wells as well. But when we check the lysimeters, maybe the first time there's no water in there. So that would be pretty interesting. In 3 months, no water went through the road. Maybe in 6 months, there's one drop. Then we can extract that drop, hopefully. We can dilute it and analyze it and see exactly what's coming out of the road. And then we can think about the broader impact that way. So this is a really unique part of this project that we haven't done in other projects where we've had a beneficial use scenario and putting something in a road base. Here's another view of the road. Hopefully you can see the groundwater wells a little bit clearer. They're very close to the road, so they're really going to be able to monitor exactly what's going, if anything, right, going under the road. But yeah, I just wanted to show you guys this so you could get an idea of the sections, and you can see that we're going to be doing a lime rock blend, then a blend with RCA, which is crushed concrete, which is a pretty valuable product, but there just isn't that much of it. So it's kind of like better than lime rock to use, but since it's in limited supply, it's not used as often. But we wanted to do a section with that because, as you can see, this LBR, the higher number means it's stronger. So the RCA blend, the crushed concrete blend, is a little bit stronger than the lime rock blend. And another thing that's important to note is that, like, lime rock on its own should have a lime rock bearing ratio of 100 or more. It's usually stronger than that, but the phosphogypsum, when you combine those, the PG doesn't actually add any strength to the blend. So really the strength of the road base, which we found when we were doing our physical tests, the strength of the road base depends on the strength of the aggregate that you're mixing it with. So that would be the crushed concrete or the lime rock. Okay, so next steps. We got our approval, we designed the road, and now we got to build it. So we got to pick up our lime rock and we got to go to the road, and that's what it looks like right now. It's a dirt road, basically, just like compacted sand. And so when we're actually doing this construction, we have to be very meticulous about how we're designing the road, because if you hire a contractor, you hire construction workers to build a road, they build roads all the time. So they're just, they're going to build the road. But actually, I'm going to be out there and Dr. Townsend's going to come with me, and we're going to make sure that this road is being built really perfectly. We need to have, exactly 50% phosphogypsum, because not only is that what we modeled and what we decided works best, but that's also in the rules and in the specifications. So basically, that's all to say that we're going to be really meticulously paying attention to how this road is built to make sure it meets all of our specs. We also have a monitoring plan for before and after the road is built. So we already started part of this monitoring plan because we have to have something to compare our results to. This is me and my friend Cassie at the road. So the road is right behind us, and there's also a well behind us that you can't see. But we were taking water from the well, the monitoring well, and testing it. And the road isn't there yet. It's just a dirt road. We don't have any PG on the road yet, but we needed to get background levels to be able to compare to later so we can say, if anything in the groundwater goes up, down, or stays the same. We're also going to be testing, like I said, the lysimeters, which are looking at any water that goes directly underneath the road base layer. And there are some physical tests too that we're going to be looking at. So here's us with the groundwater well. This is kind of funny when I show people that this is the well. It's just a pipe. And when I was first telling my students that we were going to go measure water from monitoring wells, they were imagining like a wishing well, like Jack and Jill. So that's what the well looks like. We just put the tube in there. It goes down like 20 or 30 feet, and we suck water out of it with a pump. And this is the pump right there. And then the water goes into this bucket, and we take a little sample. So we already did that. We're going to be doing it again probably next month because we need to do one more round before the road gets built. And then after the road is built, we're going to be going every few months to check what the water looks like. And if there is any changes, we'll be able to map that really closely. So in the background monitoring, similar to what we found in the risk assessment, we did find a little bit of, stuff in there just because this is at a PG site. So there was some radioactivity a tiny bit higher than what you would naturally see in groundwater. I was doing some research before this, and we found around 1, and the groundwater threshold is 5, and 1 is usually the highest you'll see in natural groundwater. And this is also no filtering, no nothing, just taking the water right from the groundwater right next to this gyp stack. There was also some iron and manganese and fluoride and sulfate, which are naturally occurring in Florida soils. That was really nothing to raise an eyebrow at or anything. Another example of radon levels. So I just said we were at 1. This chart says if you're less than 2.7, you're totally good. Usually this is in terms of gas, radon gas, but also it applies to water as well. Okay, so we're going to be doing future monitoring of the groundwater, of the physical monitoring, and we wrote out a very detailed plan. So we're very prepared to be able to look at exactly what's happening at this site over time. And we're planning to monitor this for a really long time. So right now we're thinking every few months for like 10 years. That's usually what you do when you're looking at the strength of a road, because you can't just say, oh yeah, after a year, the asphalt looks fine. That doesn't actually tell you anything. Lots of things can happen after that with the asphalt and with, durability and everything. So we're going to need to look at this for a really long time. And all of that is going to tell us what we can actually do with this phosphogypsum. And what we're thinking is that if this works, then the PG road base, that would mean the PG road base is not contaminating groundwater. It's not posing risk to human health or the environment. And we can also meet our strength requirements and keep this road in working condition so that it can be used for this project for, years to come, and then possibly in other implications as well. So long term, what we're thinking is if you can take this waste, you're imagining the gyp stack full of this like sandy, silty, not great material. Right now it's just a waste, but if we could reuse it, that means we're able to decrease our reliance on storing this stuff. So we're keeping the environment a little bit safer by taking away that risk of something like Piney Point happening again. We're also reducing reliance on raw materials. And in Florida, lime rock, which is typically what's used as a road base, lime rock has to be mined from the ground in Florida. So that's some environmental degradation there. And other materials that we can't get from Florida or even from the US, we might have to get from other countries or from other states within the US. And that means that we're using energy to transport these materials. Having this solution will encourage the growth of the fertilizer and agriculture industry in Florida. It means that we can keep doing this for years to come. And it's obviously going to reduce energy required for mining and for transportation. Thank you. That's it. Thanks for your attention. I appreciate you guys.
Okay, I have the microphone, so I get the first questions. And I have three questions. What is the radioactivity in naturally occurring Florida lime rock as you mix it with the PG?
Yeah, so lime rock has trace amounts of naturally occurring radium. So it's in that means it's undetectable. It'd be below detection limits of what we can actually test with a machine. But when you mix it at a 50-50 blend, you're having the amount of radioactivity from the PG. So you're going to be mixing it. And I think I had a slide on that where the actual measure was 27 picocurie per liter in PG on its own. When you blend it with lime rock, it's about 13 and a half now in the total blend. And the maximum that EPA was allowing was 35. So I won't go into what those numbers mean, but you can think about numbers.
Okay, thank you. And then the next is, what kind of traffic are you going to run on your road to test it? If you just build a road and don't drive on it, you're not going to learn anything. So are you going to get some big semis and drive on there and see what happens?
Yeah, that's a really good point. And we thought a lot about that. The first plan was that I would go out there for a year and just drive back and forth. And I was like, I'm going to probably not do that. I think I have better things to do. But since this road is right next to the gyp stack that's already there, there's going to be lots of trucks driving. If you can imagine the map that I showed earlier, between the plant, the phosphate fertilizer plant, and the gyp stack, they're still going to be dropping off phosphogypsum. So there's a lot of traffic. And you saw the photos of me doing the groundwater monitoring. So I've been there and been, almost hit by trucks that were driving back and forth. So there are a lot of trucks that drive back and forth on the road already that are carrying phosphogypsum. So they're like pretty heavy trucks.
Okay, and then another one is, we naturally get potholes in roads, so I'm sure you will get some, and how will you take care of that in terms of safety?
Yeah, exactly. That's a good point because a pothole means you're removing some of that asphalt layer, and the asphalt is what's impermeable. So if you had exposed road base, there would be water going through the road base. So really, it's just going to be with any other road. We're going to fill it as soon as possible, and you can very quickly fill potholes. Well, if you're the city and you have to like call the city manager, it's not so quick. But the plan for this pilot road is that we're going to be monitoring it closely, but we're also going to be making sure that this is representative of a real road. So basically, we want just as many potholes as a typical road, but also we are keeping in mind the environmental impact. So it's kind of going to be just a monitoring situation. And I truly think at the point when potholes show up, I'm probably going to be working on a different project. I'm hoping that it's going to be a long time because we're building this road to mimic other county roads. So yeah.
Okay, and then the fourth of my three questions is, uh, roads have to get recycled, and so they send in these giant grinders and rotor-rooters and grind it all up and then use it again. How does that affect your long-term look at your road?
Yeah, exactly. So since this phosphogypsum was originally in gyp stacks, it'll need to go back to the gyp stack. because it could pose direct harm. So we're either going to put it back in the gyp stack, which is kind of annoying and seems counterproductive. Hopefully, by that time, we will be able to keep reusing these materials. So instead of going back into the gyp stack, it'll get to go back into a new project.
Okay, I haven't run out of questions, but it's time for someone else. Anybody with a question? Okay, Pushpa, you're closest.
This is a wonderful project and a great presentation. Congratulations. My question is, you mentioned the heavy metals and things in water. Do you know are there known health effects of those?
Yeah. So there are health effects of heavy metals in water in general. They can cancer risk and things like that. The metals that we saw in the groundwater in the background levels, the concentration that they're existing right now are not going to pose significant health effects. Yeah.
Hi, thank you. An interesting talk and very well organized.
Thanks.
My question for you is, if you're thinking long term, like Walter already asked the one about what happens when the road's all messed up and stuff, but thinking long term, Florida, as an example, the geology is not constant everywhere. Some places are sand dunes and some places are karst and things of that nature. Do you have any thoughts as to where this would be useful and where not? You don't want like sand bases where things start to shift and or but at the same time, in my mind, you don't want karst because you get sinkholes.
Yeah.
Which just opens it right back up again.
Yeah.
So thoughts?
Yeah, that's a good point. So there's some rules when you're building a road, and there's some tests that we do to mimic like different scenarios. Like when we do that Proctor compaction and LBR test, we actually mimic a flooding scenario, which would be if the groundwater, the aquifer, rose up into the road base. That test, we have to basically prove that the material would still be strong enough and it would withstand that flooding scenario. So I would say that it's kind of unavoidable in Florida. Sometimes you have to build a road where the aquifer is going to flow up into the road base. And that is not ideal, but we already proved with our physical testing that it would withstand that physically. And then also in terms of like sand layers, when you're building a road, so you have to have the asphalt, you have to have the road base, and then below that, you have to have a sub base that still meets a certain strength requirement. And if it doesn't, you have to add something to it or change it so that it does. So if you were to just go and build a road, I don't know, on the beach where it's just sand, or anywhere else where it's just sand, you can't just put your road base right on top of the sand. You actually have to have a lime rock bearing ratio equivalent of 40. So it's about like a little less than half the strength of the road base itself. And that's the sub base layer. So instead of just putting it on top of dirt, you have to compact the dirt really well, then put the compacted road base, and then put the asphalt. Yeah.
Ask and then I'll ask. Okay. You just reminded me, I was thinking about Payne's Prairie and how 41 flooded. So you would recommend that this not be used in places that are known flooding areas? Because after all, I mean, you're saying aquifer, but I think you mean groundwater. I don't think you mean the Floridan aquifer is coming up.
Yeah.
But you don't want that leaching into all those environments.
Yeah, you're exactly right. And really, I think we can't say right now because we haven't seen this in the real world. We've only done our leaching tests in the lab, and we've seen like, okay, you get some leaching, but then if you factor in the other dilution and attenuation, you'll be fine. So I think we can't say yet, and maybe we would have to have that happen and kind of see what it looks like before we can actually make a judgment call. But right now, this pilot road is actually far above the groundwater level. Like when I was doing the sampling, we had to put our tubes down really far. So we're like 11 feet, I think, above the groundwater right now.
Jordan, that was excellent science communications. Thank you. I have a follow-up long-term question for you. Because this has such practical implications, do you have an advisory group that has direct contact with the DOT or legislators? Because this is a very thing that we hope the university would be informing best practices out in the real world.
Yeah, you're exactly right. We've done absolutely everything in our power to communicate with FDOT and FDEP. And if you guys have heard of Dr. Townsend at UF, he's very well connected. So he's got friends at FDOT that we've communicated with, and at EPA and FDEP. And then also at Mosaic, they have not only reached out to us, but they've reached out to other contractors and other consulting groups. So it's a lot of minds working together on this. And like I said, when we go out and build this road, we need to make sure that it's exactly what we planned for so that we can really test exactly what we think we're testing.
Yeah, this is kind of a follow-up to this one, that I was thinking about Paynes Prairie too. Because when you build a road, you do layer it this way, but they don't put side things on them to keep things from coming in on both sides. And you don't have to have major flooding for water to flow in horizontally too. And that's kind of my question about horizontal flow into the second layer.
Yeah, no, that's a good point. So this is a time when I wish I was a civil engineer because I would be able to answer this a little bit better. But to my understanding, the way the road is going to be built is there's the subbase, which is the existing road that's already there. And it's a well compacted like soil and sand layer. Then there's going to be the base on top of that we're creating, and that's the PG lime rock blend. And there's going to be a little shoulder of the original road before you get to the end. So kind of the original road is longer than the road that we're building. That's my understanding. And so the asphalt will be able to cover the whole thing. But this is actually a really good question, and that's why we're doing the lysimeters, because we're going to be able to, so the lysimeters are aligned. It's a plastic liner that goes underneath the base, and it's going to be kind of like overlapping the ends where we're going to be able to see any water that goes through the base at all, including horizontally, like you said. So I think that that's where that's going to come in, and the research is really lacking in that area. Like I've read a few studies where they look at water coming in horizontally, and it was actually like an unpaved road. Like that's how lacking the research is, where it's really hard to get that right now and like actually imagine what could happen. So we really only have what we've been able to model, but hopefully with these lysimeters, we'll be able to actually answer that and think about the long-term implications.
So the question was, does the liner come up to the road, and further discussion?
Yeah, so when we place the lysimeter, the liner is going to be underneath the road base layer, and all of the base layer will be on top of the liner.
My question is, what are the financial aspects of this? Who's winning and who's losing?
Yeah, no, that's a good point. Okay, so obviously, the Mosaic company who's producing the phosphogypsum, if they're able to sell the PG, they're winning. Right now, the idea is they kind of don't even care about really selling it. They just want to get rid of it. So people who are building the road, like we've actually talked with Polk County, which is where this is taking place, and they said, yeah, if this works, if the pilot project works, we would be interested in using PG in county roads, because then they don't have to buy lime rock. So they're using right now products that are very expensive, and possibly they could get the PG waste for free or for very cheap. So in that case, the county road builders would be winning. And I mean, I think it's a win for everything because I think that reusing a waste product is just a win. The Piney Point disaster, there were millions and millions of dollars of funding going into the cleanup for that. So if we can do something to prevent that and actually encapsulate this material underneath asphalt instead of putting it in a big pile right next to Tampa Bay, I think that's going to be a win for, everybody.
Okay, we have some comments and questions on chat. So first was, thank you for a full explanation. Please keep us informed of the results of your initial test. And then the next is, would it be applicable or safer in railroad beds?
I'm hearing yes. I don't know anything about railroad beds. I'm sorry. I'll have to do some research on that.
Okay, are those the only messages that we have in chat? This road will be built with great oversight. What happens when typical construction crews with little oversight build them?
Yeah.
That's a great question.
It's a good point. Yeah, it's a good point. So I guess what I meant by this is built with a lot of oversight because we already wrote down exactly what we want to test for, and the EPA approved our plan of exactly what we want to build and exactly what we want to test for. So in this particular testing situation, we need to have a lot of oversight when building this road. And depending on the results, here's the thing. If this road works, which in my mind, that means we don't see environmental contamination and the road remains, durable and good working condition, then we won't have to have the same layer of oversight in future construction projects. If we do monitor the road and it doesn't work, which in my mind, that means we're kind of like right at the cusp of like, oh, it's kind of looking weird, and maybe there were a lot of potholes or like something went wrong, whatever. That probably means that we don't do this again unless we can get a good result with a lot of oversight. So I would say that if it gets to the point where construction crews can build it without a lot of oversight, the consequences would not be there. We would basically prove that there would be no significant consequences if any regular construction crew builds it.
Wonderful. Any other questions or comments? I think I'll hire you to write my PowerPoints because that was really excellent. You gave a very detailed report in less time than we normally do, and I can take a short subject and go for over an hour. So thank you very much.
Thank you.